There is no time to waste. Me and you are competing in a race tomorrow, and we are Everyone has nice cars, but we have an old BMW. What can we do to improve it in one day? Don't worry, I have a plan. I'll unlock a little more power to some software changes, and you can add a new turbine. All of this should take less than a day. So you get to work on that turbine. But just as you are about to finish, Jeffrey comes along and asks you, "Bro, what are you doing here?" "I'm installing the new turbine, what's wrong?" "Well, I see that you use like 20 screws to fix it in place. That for sure will weigh it down, making it slower. How about use only one screw to fix it to the car?" What would you say to Jeffrey in this situation? Well, here is the thing. Screws weigh like a few grams, so a few extra won't make a difference. Having too few screws on the other hand can create problems. What if they break and the turbine falls off the car? And we'll find the ending of this story later. But you probably don't want to be like Jeffrey, right? So then, why do you apply the same mentality in programming? I see many beginners focusing on the totally wrong optimizations, instead of focusing on the important tasks. Jeffrey didn't have bad intentions, he was just trying to help. But you should always know what is the most important thing to focus on. And programming is just like this analogy. By focusing on unimportant details, you are not only wasting your time, but also potentially harming your project. There are two main ways software becomes slow and unoptimized. So in this video, I'll talk about both of them, so that instead of prematurely optimizing your code, you'll focus on the right thing and also have optimized code in the end. So, what is the thing that you need to focus on when writing your code if not optimizations? Well, there is something even more important than optimizations, and that is writing bug-free code. Like, who cares if it runs fast if it doesn't work correctly? But how can you possibly do that? Hear me out. Let's say you implement a string move function. It is pretty simple. We just copy character by character from one buffer to another until we reach the end of the string. Functions like this, however, are the number one reason security exploits appear. What if the output buffer is smaller than the input buffer? What if the input buffer is not null terminated? It's hard to write bug-free code, but there are some things we can do. Like here, we found some potential failure points. So let's make sure we cover them as well as possible. In this case, we can provide sizes for both buffers. And also, make sure to always write a 0 at the end. And this is very powerful, because first of all, if the input string is not null terminated, the size parameter will keep us safe. And just writing a 0 here is way more important than you even realize. This line basically guarantees that the output buffer is always valid and null terminated. Imagine if all your functions guarantee that they produce valid results. Your code would be unbreakable. And it is examples like this where many beginners just don't do these extra steps. Either they think it's useless, or they want to optimize their code by not doing extra checks. Here is the thing. Computers are very fast machines. An extra check will never hurt your performance. It's like the car analogy I gave earlier. A few extra screws won't hurt. This extra check, however, can save you literally days of debugging. There are many more things you can do to write bug-free code like this, and I talk about it in this video. But wait, because it's more than just these little things. Here is my Steam game. Whenever I shoot a target, these red blocks will change their state. Imagine you have to implement this. How would you do it? Maybe hold all the red blocks in a separate array. You want to know what I did? I just iterate to the entire map and check if any one of the blocks is a red block. Algorithm people would probably burn me alive. This is madness and terribly inefficient. I'm searching through the entire map instead of holding the blocks I need in a separate small array. But take a look at the game again. Do you see any lag or anything? So what is the purpose of choosing a better algorithm? To make your program run faster, of course. But it already runs fast, so it really is pointless to optimize it. And now, people will usually say, well yes, but what if your map was 1 trillion blocks big? Back to the car analogy, it's like saying, well, 20 screws for the turbine is not that big of a deal. But what if you had 1,000,000 turbines? Then it surely will be a problem. But guys, we are simply not going to add 1,000,000 turbines. And the game level will simply never be trillions of blocks. Let's just keep things simple because you might not realize it. But adding a secondary list to store the red blocks can actually add bugs and code complexity for no reason. What if it isn't synchronized correctly to the word, for example? I have one more example that I literally think is the craziest thing I have ever seen, and will convince you 100%. But first, let's talk about the two ways your program actually becomes slow. The first one is when some big important system becomes slow. Let's take this Minecraft game I'm making, for example. I could spend all day doing small optimizations, but they won't benefit me at all. You want to know why? Because the world generation system is extremely slow. So if you were in my place, what would you do? Optimize the world gen system, of course. But there is one small detail that if you get wrong, all of this video was pointless. While making your programs, don't just assume that the system is slow. Trust me, even advanced people get this wrong sometimes. This is what you should do instead. Just write your program in the simplest way possible. Don't plan for future too much. Just try to write your system. And after it is working, you can optimize it and refactor it if you need. Most of the time, however, it will be perfectly okay like it is. The second way to make your program slow is by adding very small problems across your entire system. In the car example, adding a few screws won't make any difference, but adding thousands of screws at every possible system in your car will make a difference. And I know this sounds scary and even opposite to what I said so far. I told you not to care about small details, but now I'm telling you that small details can still hurt you. Don't worry, there is one thing that you need to do, and this won't ever be a problem for you. Looking at my Minecraft game, you can see that it runs pretty well. You want to know what's crazy? This build is in debug mode, with no optimizations turned on. And I didn't do anything crazy to optimize it. I just wrote some simple code. This project shows that the methods I teach actually work. Not only does the game run well, but the development process was also smooth with relatively few bugs because 1. I kept things simple and changed them only if needed. At one point, I even replaced the chunk system with a simpler one. 2. I optimized the big important systems if they were too slow, like the world generation. 3. I added a ton of checks in the code to easily catch bugs. Like, let's say, it should be impossible for the chunk the player is in to be unloaded. Cool, let's just check that is actually true every frame. If it isn't true, we report the bug. More about it in this video. And 4. I didn't pessimize the code. And this is the thing that will make sure that adding too many screws to your car won't cause you problems. The idea is simple. So I told you not to focus on very small optimizations. But don't do very stupid things either. Don't allocate memory in the middle of the for loop if you can just allocate it one time outside the loop. Or if you use a vector in your code, reserve some size before using it. The example Casey Moratori gives usually consists in writing unnecessary complex code for simple tasks. Let's say you need to intersect a ray with a box. Please don't tell me you plan to create an abstract class called shape and then derive the box and the line and then construct the class on the heap and then use some generic polymorphic functions and then return a result collider class that's also polymorphic.
Stop it. Get some help.
This is all the code that you need to write. That's it. So I know you might be confused right now. Like, should you do small optimizations or not? Let me clarify. The rule is simple. If you can just extremely easily add that optimization, and it doesn't hurt your code readability and it doesn't make it more complex, do it. But if adding that optimization means adding too much complexity to your code, or makes it unreadable, forget it unless if it is a very important optimization. Back to the race. With this new acquired knowledge, Jeffrey spent all night mounting a Lamborghini engine to our car. It wasn't easy, but he used all the screws he could find to fix it tightly in place. The first place was ours. Now check out this video to see how you can write code so robust it catches bugs for you. Or maybe this video from Casey Moratori about not pessimizing your code. See you!